Welcome everyone to your Medical Math pre-course. This is a review for PCPs and ACPs presented by the Regional Paramedic Program for Eastern Ontario. Our agenda for today: a brief introduction, followed by oxygen cylinder capacities, a quick look at pediatric weight estimations, and then the meat and potatoes, drug expressions, single dose calculations, and IV infusions. For management's sake, we've broken up into several modules. Module 1 will deal with oxygen cylinder capacities. But first, an introduction. The material being presented today should be a review for everyone. There's absolutely no new information being provided. All of this material was covered during your PCP or your ACP college programs. And don't worry, the rules of basic math still apply. Everything you learned in high school about addition and subtraction, multiplication and division are still there. There's nothing tricky. There's nothing complicated. Don't worry just because we happen to be working with medications or patients. It's still just basic math. That doesn't mean we can let down our guard though. We do need to be careful because we know that most medication errors are an error by a factor of 10. And that, of course, is a misplaced decimal point. A factor of 10 can be a costly error when we're dealing with medications, and sometimes it could even be a fatal one. So we do have to take care when we're doing our medical math. But at the same time, it's still just basic math. Let's dig in to something that's maybe not as dangerous as some of the medications: oxygen cylinder calculations. A cylinder under pressure holds a volume of gas. I think we know that. But when pressures are involved, we're talking about larger volumes of gas than could simply fit inside a cylinder at 1 atmosphere. Different size cylinders hold different volumes, but it's not a 1-to-1 ratio either. We can take an M tank and stand it up against the wall. And we can hold up a D tank and we can estimate that a D tank would fit inside the M tank 8 or 10 times. However, it's not as simple as that because we have pressures involved as well. The larger the tank, the even higher volume of gas that can be accommodated inside that tank at a given pressure compared to a smaller tank. Let's figure out how to determine what that volume is. We have a formula here. Cylinder pressure times tank factor equals that gas volume. And if you're worried about remembering tank factors, don't worry. I've got them for you on the next slide. Cylinder pressure is measured in pounds per square inch. And that comes right off the gauge on the tank. There's nothing exciting about doing that. We just look at the gauge and we determine what that cylinder pressure is. Here are our tank factors: 0.16 for a D, 1.56 for an M, and then the result of our calculation is gas volume measured in liters. Now hold up. I know we're dealing with a mixture of imperial and metric. We've got pounds going in and liters coming out. Don't worry, the tank factor looks after that calculation, looks after that conversion for you. So let's look at our example. You have a portable oxygen kit with a full D tank at 2,000 pounds. Hey, that's how I like to find my D tanks when I come into work in the morning. How much oxygen is available in that D tank with 2,000 pounds for your patient's use? So let's use our formula. 2,000 pounds times 0.16 as a tank factor equals 320 liters. That sounds like a lot of oxygen. But you're probably all ready to stop me and say, hey, that's not all available for our patient because we never let a D tank get completely empty, do we? So let's consider a safe residual pressure. In practice, we hold back about 500 pounds as a safe residual pressure because we never want to let that D tank go completely empty, particularly if we have a patient who is in the middle of using it. We generally don't want to let them run out of oxygen, particularly if they're kind of dependent on it. So we hold back about 500 pounds. We say 500 pounds is the end where it's time to change. And that gives us a little bit of wiggle room if we're not 100% ready to actually change the tank right at that second. The second item is more of an oxygen supplier problem, but we never want to let tanks go completely dry. As soon as you let every drop of pressure out of that tank, there's an opportunity for moisture to get inside the tank, and that's a problem for the suppliers. So we try to help them out and not let the tanks go completely dry. And then item number 3, most pressure regulators on the market will not provide the desired oxygen flow rate if the tank goes below 500 pounds. And that number varies from manufacturer to manufacturer. But on average, 500 pounds is about the number that's the basement that the pressure regulator manufacturer wants you to go. Below that, they cannot guarantee that you're getting the desired oxygen flow that you think you are. So 3 good reasons why we should not let our tanks go below 500 pounds. So let's take that 500 away. Instead of 2,000, I'm going to use 1,500 times our tank factor equals 240 liters. That's still a lot of oxygen, but I don't know how long that'll last. Let's figure out how long that will last. We got one more small calculation to do. We need to divide that amount of oxygen by the flow rate, which would be in liters per minute, and that will equal the amount of time we have available. So let's take a look at our example. I've got 240 liters that we already calculated. I'm going to divide by 15 liters per minute. The second question asks, how long will the oxygen kit last at 15 liters per minute? So let's plug it in. Answer, 16 minutes. That's a pretty decent number. I'm not entirely happy with it, but I can work with it. But keep that one in mind, because this is probably a real common scenario you're going to encounter in your career. You're going to come in the morning, you're going to change out for a brand new D-tank at 2,000 pounds, and your first call of the morning is going to be a cardiac patient who needs high flow O2. So there you go. High flow O2 patient, 15 liters per minute. I got 16 minutes before I need to get that patient onto another D cylinder or out to my truck on the M cylinder. So take that 16 minutes, put it in your back pocket, and keep it in mind. It might come in handy. But enough of an example. Now it's your turn. I've got 4 questions here. A particular tank with a particular amount of pressure left in it, and then a desired flow rate. I want you guys to calculate how long you can deliver that desired flow rate before you run out. I've got your formulas there. I've got your tank factors there. Don't forget to remove 500 pounds as a safe residual. Go ahead and pause the presentation right now. I'll be waiting for you when you get back, and then we'll take up the answers. All right. Okay, welcome back. Let's see how you made out, see if your answers agree with mine. Question number 1 asked, with an M tank at 1,800 pounds delivering 12 liters per minute, how long can I deliver the desired flow? Here's my calculations, see if you agree. 1,800 minus 5 times a tank factor of 1.56 equals 2,028 liters. Divide that by 12 liters per minute, I get 160 minutes. I couldn't be happier with that number. I can get a patient to the hospital in under 160 minutes. Unless I got a really long transport time, I think I can do it. All right. Question number 2. A D-tank with 1,000 psi delivering 4 liters per minute. A little oxygen through a nasal cannula. Let's see how we do. 1,000 minus 5 times a tank factor of 0.16 equals 80 liters of oxygen. Ooh, that's not as much as the last question, but it is a smaller tank. Let's finish it off. 80 liters divided by 4 liters per minute equals 20 minutes. That's not a great number, but I can work with that number. I can assess a patient and get them out of the house in under 20 minutes, unless there's something complicated going on. But generally, if I'm delivering 4 liters per minute, 20 minutes is plenty of time for that patient. I can do that. Number 3, an M-tank with 2,000 pounds left delivering 10 liters per minute. A brand new M-tank. The crew who just finished their shift must have changed it for you. Wasn't that nice? 2,000 pounds divided by, minus 5 times 1.56 equals 2,340 liters. I like that number. Divide that by 10 liters per minute, 234 minutes. That is a great number. That is a really long transport time, and I still have oxygen flowing. I like that. Number 4. Ooh, I don't like where this is going. A D-tank with 800 pounds left delivering 15 liters per minute. I'm not liking that at all. That's the one where you're thinking, gee, the tank's getting low, but I can probably get one more call out of it. But that next call was a cardiac call. 800 minus 5 times 0.16 equals 48 liters. Ooh, that's much lower than the other ones. 48 liters divided by 15 liters per minute equals 3.2 minutes. Yikes. I don't know about you, but I can't think of too many patients in my career where I've assessed them and got them out to the ambulance in 3.2 minutes. Not unless they met me at the end of the driveway. So keep that one in mind next time you're getting low and you think I can get one more call out of it. So hopefully your answers agreed with mine. That'll finish up Module 1. Go ahead, whenever you're ready, start on Module 2. We'll cover weight estimation for the peds, and we'll get into some drug expressions.